In this video, we're going to go over the proof for Urysohn's lemma, which is a different way of looking at the separation of different sets within a normal space. So what it says is that assume X is a normal space and let A and B be disjoint closed subsets of X. Then there exists a continuous function, f of X, mapping elements of X to this closed interval A to B on the real line, such that f of X is equal to A for every X in A, and f of X is equal to B for every X in B. So what this would look like schematically is that for all the X values in this closed subset of X, if you imagine projecting down their values to this function f of X, then we'll have that it's constant for all of these X's, and they all map to this value A. And then the same goes for B, where all the values are going to map to B here. And to see how intuitively this says something about separation of sets, what's happening is that when you actually make that transition, because whenever you choose an interval on the real line, B to A, there's going to be some gap here. And you want to make sure that your continuous function can climb that gap in a way that's continuous, which tells you that for any open interval here, you have a smaller open interval in the domain, such that if X is within here, you know that your function is going to be contained in this open interval over here. And of course, when you look at it this way, then you start to see, okay, so there's some way that we can separate these two closed sets by open sets. And this follows from the space being normal, but it ends up being a very useful a useful theorem or a useful lemma to prove a bunch of other important results and theorems in topology. So we're going to be going over the proof for this. We're going to first discuss the plan for how we're going to do it, and then we're going to execute this plan step by step. So firstly, we're going to restrict our attention to this closed interval, 0 to 1. Since any closed interval on the real line is homeomorphic to one another, we can just focus on 0 to 1 to simplify things and not introduce any unnecessary complications. And secondly, we're going to use the fact that this space is normal to define an open set U of P for all P in this countably dense subset of 0 to 1. And we need to use a countably dense subset here for two reasons. Firstly, we need it to be countable so that we can define U of P inductively, and then we need it to be dense so that we can actually construct a surjection in terms of these sets. And these sets that we're going to construct need to meet a particular property. In particular, we need that P less than Q, where P and Q are both part of this subset. This should imply that the open set for P is contained in the open set of Q. Or excuse me, the closure of the open set corresponding to this rational P. And the result of this is that we're going to have a countable collection of sets, of open sets, that are simply ordered by inclusion. And that ordering corresponds to the way these rationals are ordered on the real line. And that's going to turn out to be useful for us when we're trying to prove that the resulting function is continuous. And that's going to be step 3, which is prove that f of x is continuous. And I haven't said anything about what f of x is going to be, but it's going to depend on our definition of these open sets. So let's begin. We're going to start by defining these open sets U of P. And in order to do this, we want to make use of this equivalent definition of a space being normal. So we can recall that a normal space X has the property that for any two disjoint closed subsets A and B, where they are disjoint and they're closed, means that we can find U of A, which is an open set containing A, and U of B containing B such that U of A intersected with U of B is also the empty set. So these two sets are also disjoint. This is the definition of a normal space. But there's an equivalent definition where for any open set U and a closed set contained in U, we can find an open set containing A such that the closure of this open set V is contained in U. And these two definitions are equivalent. The proof is not so hard, but I'm not going to do that here. I'm just going to start using this definition.